Welcome back. So this week it will mainly be a preparation of two types of classifications that we'll do in the last 2 weeks of this course. So these are the classification of representations of SU3 and some applications to particle physics. And also the classification of all compact Lie algebras that we'll do in the last week. And both of these, and also the representations of other Lie groups, it relies on some structure that we can discover within the Lie algebra of a Lie group. And really what we're going to do is we're going to formalize the notion that we already applied for SU2, where we selected one of the generators of SU2 to diagonalize, and then we studied the eigenvalue structure of this diagonal generator in order to completely classify the possible forms of these generators. So what we would like to do in general for a larger Lie algebra is to diagonalize as many generators as possible. And really, the Cartan subalgebra, it formalizes kind of the choice of a maximal set of diagonalizable generators. So let me write this. The Cartan subalgebra formalizes in this notion of choosing a maximal set, so the maximal choice of simultaneously diagonalizable generators for the Lie algebra G. Then, as soon as we have these diagonalizable generators, we can again look at the eigenvectors and the eigenvalues of them, and they will tell us something about this Lie algebra. And actually, they tell you everything that there is to know about this Lie algebra. So to make this mathematically precise, first let me tell you what a subalgebra of a Lie algebra is. So here's the definition. A subalgebra of a Lie algebra G, it is a linear subspace. It's denoted by H of G that satisfies that if you take two elements in a subspace, that the Lie bracket of these elements is again in the subspace. So it's saying that the Lie bracket closes on this subspace of generators. So sometimes we also write this as taking the Lie bracket of these two subspaces being a subset of this subspace again. Right, so this is really the mathematical notation of taking the image of all possible choices of vectors from the subspace H. And all of these have to lie in H again. Okay? So a very simple subspace would be if I have a number of generators, H1 up to HR, in the Lie algebra G, and if they commute, so meaning that the commutator, the Lie bracket of HI with HJ is 0, then okay, they trivially span a subalgebra simply because taking any Lie bracket of a linear combination of these elements is going to vanish. So, and the 0 vector is always in H. So this is certainly a subalgebra. So essentially that's what the Cartan subalgebra is, except that we have the additional requirement that it's maximal. So it should be a maximal set of generators that pairwise commute with each other. So a Cartan subalgebra H of G, it is a subalgebra that satisfies that if I look at all possible commutators of elements in H, that they all vanish. So it's a maximal commuting set of generators that satisfy this and is maximal where, okay, let me be precise about what maximal means. So maximal just means that if I have another vector in the Lie algebra G that commutes with all of the vectors in H, then I really want this vector to be part of the Cartan subalgebra. So this is saying that if a generator in the Lie algebra satisfies that the commutator with all of the elements of H is 0, then I really want X to be in H. So that's a maximality property. So the way to find the subalgebra is the Cartan subalgebra is just to take your first generator, which is going to commute with itself. So it spans a subalgebra trivially. And then I look for another generator that commutes with this one. Then I add it to this subalgebra, making it bigger. It's still going to commute with itself. And then I keep on adding vectors until I can't find any new generators that commute with all of them. And then I found the Cartan subalgebra. Now, the fact is that that any two Cartan subalgebras are actually equivalent to each other. So all Cartan subalgebras are equivalent. So in the sense that one can do a basis transformation that maps one to the other. In the sense that they are related by a basis transformation that preserves the structure of the Lie algebra, so that preserves the structure constants. That preserves structure constants FABC. So one does not have to worry really about what vectors we start with. As soon as we have found a maximal set of generators that commute, then it's as good as any other such set of generators. And in particular, I mean, the number of such commuting generators that one can find is independent of each choice. So here really the index r, the maximal number of these, it is a well-defined number that I can associate to the Lie algebra. And this is called the rank of the Lie algebra. So definition, the rank r of G, it is really the dimension of your Cartan subalgebra. And a basis of this Cartan subalgebra, H1 up to HR, is called the set of Cartan generators. It's called Cartan generators. Okay. So now what we'd like to do is to choose within your Lie algebra some set of Cartan generators, and assume that they are Hermitian, because then we can simultaneously diagonalize them, and the eigenvalues of these, or the values that appear then on the diagonal of these generators, are going to be real numbers. But we have to be slightly careful here, because what we said is that for most Lie algebras that we have encountered, so in particular the special unitary Lie algebras, but also the special orthogonal ones, the generators, so all elements of the Lie algebra G, are actually skew Hermitian, while we prefer to work with Hermitian operators. And not only that, we also like to work with like raising and lowering operators, as we did in SU2, and they are neither skew Hermitian nor Hermitian. They are given by a linear combination with some complex coefficients. So they're not actually part of the Lie algebra. So here's just a quick remark that implicitly we will be working not really in the Lie algebra itself, but its complexification. We're working in the so-called complexified Lie algebra. So what is a complexified Lie algebra? Well, mathematicians would denote this by a subscript C for the complex numbers. It is simply linear combinations of the basis of generators, but where we now allow the coefficients to be complex numbers. Whereas the standard Lie algebra, we were only allowing real linear combinations of these generators. And when you're working in the complexified Lie algebra, where we're allowed to have imaginary coefficients, then it's much easier to do the linear algebra, because one can always find eigenvectors in this space, although they may not live in the actual Lie algebra itself. And also, this allows us to not choose this basis of Cartan generators to be Hermitian, simply because if I have a skew Hermitian set of generators, then just multiplying them by I makes them Hermitian. This allows us to choose Cartan generators to be Hermitian. So I won't be mentioning this explicitly from now on anymore. But you should keep in mind, whenever I write the Lie algebra in the next couple of lectures, that I'm usually allowing complex coefficients. And typically I'll take all the generators that I'm looking at, so both these Cartan generators as well as the non-Cartan generators, to be Hermitian. And there is no problem in actually doing so in this complexified setting. Okay? Now as soon as we have commuting Hermitian matrices, then I can simultaneously diagonalize them. So I can choose a basis of states. Let's denote them mu x, where mu is a vector mu1 up to mu r, consisting of r real numbers, and x some additional quantum numbers, additional labels, such that if I act with my Cartan generator on this state, it is going to have an eigenvalue, so it's diagonal, and I label the eigenvalue of the ith Cartan generator by mu I. Okay, and these set of r-dimensional vectors, they are called the weights of this Lie algebra in the particular representation that you're looking at. So these are weights, and they depend on the representation of the Lie algebra G. And of course on your particular choice of Cartan generators. So just a quick example. So why do we call this weights? Well, this sounds familiar from our SU2 lecture. So example in the case of SU2. So there, what is the Cartan subalgebra? Well, we have to choose generators that commute with each other, but we already noticed 2 weeks ago that if one chooses the first Cartan generator to be J3, then well, there are no other generators that commute with this. So this really is the maximal commuting subalgebra, meaning that the rank is equal to 1. And what are the weights in this setting? So the weights, they are the eigenvalues of J3. So they run exactly from minus J up to J in the spin J representation. Or if you look at a more general direct sum of spin J representations, it can be a larger set with some multiplicities for these weights. Okay? So what we're going to do next is to use this Cartan subalgebra and its diagonalization in terms of the weights applied to a very particular representation, which is the adjoint representation that we saw last week. Okay. And this will really be our starting point for classifying Lie algebras. So, the rest of this lecture, we will focus on the adjoint representation. So recall from last week that the adjoint representation of a Lie algebra is a representation that acts on the vector space that is the Lie algebra itself. So if I have two generators x and y in the Lie algebra, then I can consider the action of x on the vector y given by exactly the Lie bracket of these two generators. And we've seen that this determines a genuine representation, so the matrix elements corresponding to this this action, they really satisfy the commutation relations of the abstract Lie algebra G. So what does this mean for the Cartan generators? So note that by definition the Cartan generators commute with each other. So that means that in the adjoint representation the Cartan generators are annihilated by the other Cartan generators. So Hj is a state of weight 0. Okay, so you should think of this as the 0 vector in RR. And conversely, if you have some general generator Y that is annihilated by all Cartan generators, so meaning that it has this weight 0, then it has to be part of the Cartan subalgebra by the maximality criterion. So we can divide our generators of the Lie algebra into the Cartan generators and the generators that have non-zero weight. And these non-zero weights are called the roots. So definition, the roots of G are the non-vanishing or non-zero weights. And okay, for now we're going to denote them by alpha. So alpha is going to be a vector with r components. not Rn, RR. And it's not allowed to be 0, so without 0. These are the roots of G. Okay. So since the we have diagonalized the Cartan generators, we can find the basis of states of our Lie algebra in which it's acting, that are all eigenvectors of Hi. So we can always find a basis of G of the form, well, we have the Cartan generators Hi, so these are the vectors with 0 eigenvalues, so 0 weight. And then there are the roots, because those are the ones that have the other weights, the non-zero weights. So the set, and let's denote these vectors by E alpha, where alpha ranges over the roots of G. Okay, and they diagonalize the Cartan generators of the form that diagonalizes Hi, meaning that if I act with Hi on Hj, well, as we just said, that is 0. And if we act on one of these root vectors, then by definition they're going to have the eigenvalue alpha I. So we said that there are R of these, but we also know that the dimension of the Lie algebra, so let's denote that by n. Well, if this is a basis, then there have to be exactly n basis vectors. So there will be exactly n minus r roots. So what we're going to do is try to make sense of what these roots can be in order to group up into a well-defined Lie algebra. So let's make some observations. Well, the first thing that I would like to say is the following. So we will see that there are no degenerate roots. So this is already kind of implicit in my notation E of alpha. So there are no degenerate roots in the sense that for each alpha there is only one state E alpha satisfying this condition. So that means that up to some multiplicative factor, our choice of these basis states E of alpha is really unique. And let's give some interpretation to these states E of alpha. So what does this condition mean for the commutator of Hi with E of alpha? Well, I mean, this action is just a commutator, right? So this is saying that hi commutator with E of alpha is alpha I E of alpha. And this smells very familiar to what we've seen for SU2, where we had a J3 here, and then say J plus, where the commutator of J3 with J plus was J3 again. So here too, these E of alpha have an interpretation of a raising or lowering operator. So this is like a, let's call it a raising operator, although it's going to raise in a particular direction. In what sense? Well, let's have a look. So if I look at an eigenvector of the Cartan generators, so E alpha prime for some root alpha prime, and then act on it with this operator E alpha, then I claim that it's an eigenvector again. So let's see. So if I act with hi on this, and this is really the same exercise that we did for SU2 to see that J plus and J minus change the eigenvalue. What we do is we're going to insert here this commutation relation. So we get that this is E of alpha hi plus alpha I E of alpha but by definition E of alpha prime is an eigenvector of the Cartan generators. So this is alpha I prime plus alpha I acting on E of alpha prime. So if this part does not vanish, then we have actually found, again, a simultaneous eigenvector of all the Cartan generators, but now with weight alpha prime plus alpha. So essentially there are three options for this particular state, E of alpha acting on E of alpha prime. So this is really the commutator of E of alpha prime. So what are the three options? Well, it can vanish if these commute with each other. It could be proportional to a state E of alpha plus alpha prime if alpha plus alpha prime is not equal to 0. So if alpha plus alpha prime is not equal to 0, then that means that this must be your root. So there must be a corresponding basis vector, E alpha plus alpha prime. But it can also happen that alpha plus alpha prime vanishes, but that means that this has to be part of the Cartan subalgebra. So then this is really part of the Cartan subalgebra H, so it will be some linear combination of the Cartan generators hi. Okay, and here's another observation. So let's take the Hermitian conjugate of this formula that I write here. Then what do I get? Well, I get, if I take the Hermitian conjugate here and we assume that hi is Hermitian, then because I take the conjugate, the factors here will swap. So I get a minus sign. So I get that minus hi e alpha dagger is going to be, well, this is a real number, so it does not change. And then I get e alpha dagger. So put differently, let me put the minus sign here. So what we see is that h of I acting on the Hermitian conjugate of this particular state, it has weight minus alpha. So it is a state corresponding to the root minus alpha. So it must be proportional to actually the basis element there, and we can choose the normalization of the basis state such that e of alpha dagger is really e of minus alpha. Okay. So that is one thing. Let's do two more remarks. What we can also do is say, well, since these are Hermitian, so they are Hermitian with respect to the following inner product, the basis states hi e alpha can be normalized to be orthonormal with respect to the Cartan killing metric so that is the metric that we saw last time, given by the trace of x, y, except, and this is slightly different from what we've seen before, that we're going to put an Hermitian conjugate on the x. And this is really a consequence of that we're working in the complexified Lie algebra. So as long as we're in just real linear multiples of the generators, then this Hermitian conjugate is not going to appear non-trivially. But if we're working with complex multiples, then we would really like this inner product to involve a complex conjugate in its left-hand side. Okay. So this is all a bit abstract. So let me go back to our example of SU2 to show that this is really what we did for SU2. So we said that, so your example, so SU2, it had rank 1, and our Cartan generator was J3. And in the adjoint representation, so recall this is the spin 1 representation, it has 3 eigenvalues, So let me just draw them on the line. So this is the line of h1 equal to j3, or its diagonal values if you like. It has 3 eigenvectors in the adjoint representation. And what are these eigenvectors? Well, there is a 0 eigenvector, which is just j3 itself. Then there is the 1 eigenvector, so with root equal to 1, and this is, so this we would denote e1, but it was just a j plus, and here we have the e minus 1, which is the j minus. And indeed, if you check, I mean, these commutation relations that I wrote down here, they exactly correspond to the commutation relation between j minus, j plus, and j3. So we had a 3-dimensional Lie algebra SU2. So the basis is given by its single Cartan generator H1. So that means that there have to be 2 roots, and these 2 roots exactly correspond to j plus and j minus. Now for more general Lie algebras, the rank will be larger, so this diagram will look slightly more complicated. So here is an example of SO5, so the special or orthogonal group in 5 dimensions. So this one has dimension equal to 10. It has rank 2, so there are 2 Cartan generators. And we can actually draw the roots corresponding to this. So now there will be 2 axes, one labeling the eigenvalues of the first Cartan generator, second one for the second Cartan generator. And then, well, there have to be 8 remaining basis states, so 8 roots in here. They're all distinct. And what are these roots? Well, they take the following form. Like this. And here's a nice fact that we're not going to prove. The set of roots, so just these, in this case, 2-dimensional vectors, set of roots, so in RR, completely determines the corresponding compact Lie algebra. So as soon as we see a picture of all the roots of a Lie algebra, one can actually completely work out what the structure constants are going to be, and therefore determine the abstract underlying Lie algebra belonging to this picture. And actually in the exercises you'll do this exercise pretty much completely. So I'm going to give you the picture of the roots of SU3. So in exercises I give you the roots of SU3, and you're going to work out the commutation relations of the corresponding generators. So there will be 2 Cartan generators and the root states.